All right. This is exciting, guys. Oh, man. Hope you have your blades of grass. Oh, I could not think of that word blades earlier when I was typing that. Or got a bunch of spaghetti sitting around, uncooked, by the way, preferably. Maybe you have a bunch of toothpicks lying around, or some skewers, or, something that is straight and breakable to specific lengths. Because I'm screencasting, have a segment that I can choose the length of. I also have some chicken on the grill. We're doing some pad thai, pretty exciting. And yeah, getting ready here, just cleaned up the kitchen. So let's talk through the graph of sine and cosine. You're gonna build this today, and that's pretty exciting. So I asked you to create a piece of graph paper. You can't create paper. Means other people, maybe someday you will be like a paper creator. But for now, go grab a piece of graph paper, and asked you to label the x-axis as so, -3 pi to 3 pi, and each tick mark square is worth 30 degrees or pi over 6. Okay, so that would put pi over 3 here, which would be 60 degrees. And that does put pi over 4 right in between there at 45 degrees. I originally was going to have you guys go by 15s, but I realized the paper wasn't wide enough. Notice that my y-axis isn't labeled yet. I'm going to ask you to make sense of how to label the y-axis in the lesson today. You'll notice that the x-axis is labeled as theta. So we are inputting an angle measure, and we are outputting, well, actually I'm going to leave that here, but I'm going to let you interpret it differently later on. So we've got the sine of x, and so we've got an input of a radian or an angle measure. Well, it's an angle measure in radians, so let's actually do that. So it is an angle measure in radians. You might have noticed I switched to degrees when I was just talking. I just have a tendency to move between the two fluently, and my language, my verbal discussion, because I personally prefer degrees. Like they just make more sense in my brain. But radians are, I guess mathematicians find them more useful. I think, with the whole circumference thing, it's got a distance, it's an arc length, and an angle measure, so it's got a little bit more fluidity out there in the mathematics world. So that's why most mathematicians use radians, and I'm comfortable using them, but just realize you can transition back and forth as long as your final answer is in radians. We got an output here of a ratio of sides, but you're probably going to think about that a little bit differently as well today. So the task is going to ask you to find the length of the opposite side at various radian points. So the first one being, how tall is your triangle, your right triangle, at pi over 6? Or how big is the opposite side length? And remembering from our synchronous class, we're really, since we know that this is just 1, we know sine is opposite over a hypotenuse, but if you're dividing by 1, dividing by the hypotenuse becomes non-existent almost. When you divide by 1, nothing changes. We can call it an identity operation. And so we're just gonna be thinking about the opposite side length or the height of this triangle today, because that's all we need for sine. So it's asking you to take a stick of spaghetti, blade of grass, whatevs, and make it so that it is the length from the positive, or from, not necessarily the positive in this case, yes, from the x-axis to the top of the triangle or to that angle measure, so where it opened to, okay? So I'm just going to take this spot here, and I'm going to copy it, and I'm going to place it on my graph at pi over 6. So what this is this is the length of the opposite side length at pi over 6. So what I'm ultimately generating here is a coordinate point. Okay? And we want you to do this for every single angle measure. So let's take a look at this next one here. So how tall is the triangle at pi over 4? Or how big is the opposite side length? I'm not sure why that didn't lock. Let's try that again. There we go. So again, I would take a stick of spaghetti, lay it on the unit circle, find out how long it is. In my case, I'm going to copy it. I'm going to move it down here to pi over 4, and I'm going to paste it. And again, now I have this coordinate point representing that opposite side length for sine. Oops, that's actually in the wrong spot because I said I did pi over 4, so bam. All right, halfway between. Perfect. All right, and then let's do another one. Let's do this green. So how long is the opposite side length at pi over 3, or our sine value? Again, I'm going to copy this length. I'm going to bring it down, and I'm going to place it on pi over 3. Beautiful. I've got myself another coordinate point. I'm going to repeat this process over and over and over again. Even on the quadrantal angles. Bam. Probably way more fun actually with spaghetti than it is with notability. However, I do love notability. Okay, got that down, and I'm creating another coordinate point. And as you do this, you're going to work yourself around the unit circle, and you're going to start to see a pattern growing. And you're also going to start to see the sine graph form. So we're asking you to do this for every single angle measure on this unit circle. So how tall is it here, here, here? Boom. Oops, missed one. Boom, 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 boom. So we did these 4 together. I need you to do the rest. Except let's do one together that's like negative or something. Like this guy. Whoa, here I am. Okay. Okay, so 4 pi over 3 copy. There we go. So that is, let's see, got to think outside here. So this would be 270, so I'm back 30 degrees from 270. So 270, so back 30 degrees from 270. That should put that guy. Whoa, why isn't that? That's not a straight line. You get the gist, though. I'm not going to redo that. So then you get your coordinate point, and we are good to go. Actually, we can just redraw it. Or not. This is going well, I think. I think it's going well. What do you think? Okay. Oh, wait. That's not right. That's not right. Because this guy, remember from the other day, this is actually negative. So we actually need to take this and move it this direction. So we do want to show that that is actually a negative length. So we need to go below the x-axis to show that. So you're going to notice that in this, when you're in this lower quadrant, these lengths are going to be below the x-axis, whereas our lengths that are in the upper 2 quadrants are above the x-axis. So do think about directionality as you work through this today. Okay? So we're asking you to build the sine and cosine graph with spaghetti. It's kind of fun. No, that wasn't what I wanted back. I wanted this green line back. There we go. Okay. All right. That's super fun. And I also want you to think about like what you're gonna label this. Like, what are these? Because they're not just like y values, but what are they? What do they represent in relationship to sine? If this is a sine function, what are these outputs? And I'm looking for something different than a ratio of sides. I want something more specific, more personalized. You know, let your personality shine on that. Okay. Super fun. You can always check yourself at the end of the lesson. Don't forget to check and reflect on your thinking. Now, similarly, we're going to ask you to think about the cosine graph. And the cosine graph, super duper fun. Like when I zoom in lately, my little zoom box disappears. So we're looking at cosine of x. We still have an input of an angle measure. Whoa. And we have an output. Again, of a ratio of sides, but I am asking you to be a little bit more specific and personalized when you go to label your y-axes, so that it just kind of connects a little bit more to cosine. Now, remembering from our synchronous lesson here that our cosine values are showing up in our x coordinates. It also showed up as our adjacent side lengths, or what I like to call the width of the triangle. So it might be helpful for us to get a little bit, I can eyeball that actually. Let's just get rid of those. So how wide is the triangle, or how long is the adjacent side? And then this is kind of weird. This is where the spaghetti is so much easier than notability. So I need to take this width and place it here, but I need it to be this, whoa, how come you won't rotate? This way. And I know that I changed the size of it in that moment, which is kind of the bummer of that whole idea. But you're going to take what was the width and make it this, so you can locate that coordinate point. So the length of that spaghetti strand is the output. So if the spaghetti strand was this long, then that's the output on your cosine graph. You may notice here on this very first spot, its distance is 1. So that might be where we somehow figure out where we want 1. So on this graph, it's all looking at the width of the triangle, and then you take the width and turn it so that you can find the output, which is the length of the adjacent side. And then as you do that for all of the angle measures, oh, and don't forget 0. And 2 pi. If you were to connect the tops of all of the spaghetti strands, what would the graph look like? That's your task today, is to make sense of why the sine and cosine graph look as they do. And another fun thing to think about is, why are they called circular functions? Because when they're drawn, they're played out horizontally, like from here to here. But they're still called a circular function, which is super interesting. So it's a fun little interpretation. I hope you guys have a good time. I should probably go check on my chicken and make sure it is not burning. I hope you have a wonderful evening or day, or whenever you watch this, you just have the bestest time in the whole wide world. Thanks so much for being here. Talk to you later. Bye-bye.